Hello everyone, now we will have a tutorial session and in this class we will solve some numerical problems based on our last 4 classes. Problem number 1, statement is 1 gram of a MSW sample is heated at 105 degree centigrade for 24 hours and the weight of the dried material is found as 0.9 gram, which is further heated in a furnace at 950 degree centigrade for 7 minutes in absence of air by putting the lid of the crucible. The weight loss is found at 0.3 gram. The remaining material is cooled with lid cover. When the temperature reaches to ambient temperature, its lid is opened and it is further heated in an oven at 750 degree centigrade for half an hour in presence of oxygen. After cooling the material, the residual mass of the material is found at 0.14 gram. Determine the moisture content, volatile matter, ash and fixed carbon of the waste. So, this problem is a proximate analysis, a case of proximate analysis, and we can solve it as per our discussion in the previous class. So, here we have initial mass is equal to 1 gram and then moisture content is how much? The first one is moisture content, which is heated at 105 degree centigrade for 24 hours. So, the dried material is 0.9. So, the remaining 1 minus 0.9. So, that is our loss. So, that is the moisture. So, 1 minus 0.9 divided by 1 into 100. So, 10%. So, 10% moisture we are getting. Then heating at 950 degree centigrade for 7 minutes, that loss will be related to the volatile matter. So, volatile matter content is equal to 0.3 because this loss is 0.3 directly given. So, 0.3 by 1 into 100. So, that is equal to 30%, and after that, after heating at 750 degree centigrade for half an hour in presence of oxygen, the amount which is remaining, that is our ash content. So, the ash content is 0.14 by 1 into 100. So, 14%. Now, by difference we will get the fixed carbon. So, fixed carbon is equal to 100 minus ash content minus volatile matter content and minus moisture 100 minus moisture content minus volatile matter content minus ash content. So, we are getting 46%. So, fixed carbon is 46%. So, problem number 2, the statement is an industrial wastewater is tested for measuring BOD5 value. The wastewater is diluted 100 times with dilution water before it is used in the test. The DO of one real and blank sample are determined, which is 10 ppm. Other 2 BOD bottles filled with real and blank samples are incubated for 5 days at 20 degree centigrade. After 5 days, the DO value of the real and blank samples are found as 3 ppm and 9.5 ppm respectively. Calculate the BOD5 of the original wastewater sample. If 5 ml of microbial seeds are used in the preparation of 300 ml dilution water, how the BOD value will differ? So, this is the problem based on the determination of BOD. So, we have the formula. So, BOD5 in mg per liter equal to D into DO T equal to 0 minus DO T equal to 5 for sample minus DO T equal to 0 minus DO T equal to 5 for blank, where D is the dilution factor, in this case 100 times dilution. So, D is equal to 100 and DO T equal to 0 for sample, that is equal to 10 ppm, and it is given, this is for both real sample and the blank test bottles, and then DO T equal to 5 for real sample test is also given, that is equal to 3 ppm, and DO T equal to 5 for blank test is 9.7. So, BOD5 in ppm is equal to D into DO T equal to 0 minus DO T equal to 0 for the sample as given here, minus DOT equal to 0 for the blank minus DOT equal to 5 for the blank. So, 9.7. So, this is the formula and we are getting the value of 670 ppm. For the second case, when seeding is done, in that case D is the dilution factor and F is there, another factor is there that we have to consider. So, F is the ratio of seed volume in dilution solution to seed volume in BOD test on seed, and normally it is near to 1, we have discussed in our previous class. Now, here we will see. So, as per the statement, seed volume in 200 ml dilution water is 5 ml and for 100 time dilution 3 ml real waste water sample is added with 290 ml of dilution water. So, 297 plus 3, that is equal to 300 ml you are getting. So, this is our sample, this is diluted water. So, the volume of seeds in the real oblique test sample is equal to how much? 5 divided by 300 into 297, because seed volume in 300 ml we have 5 ml of seed volume. 300 ml dilution water contains 5 ml of seed volume. So, 297 ml will contain 5 divided by 300 into 290 ml of seed volume. Therefore, we are getting here F equal to 5, which is available in the dilution solution, 300 ml dilution solution, that is equal to 5 ml. So, 5 divided by 5 into 297 divided by 300. So, 5 into 300 by 5 into 297, that is equal to 1.01. So, that is why F is near to 1 we have mentioned. So, in this case BOD will be slightly different from the first case, that will be we have to multiply it by 1.01. So, we have 100 into 10 minus 3 minus 10 minus 9.7 into 1.01, that is equal to 669.1 ppm. Problem number 3. The statement is 2 gram of a dried agricultural waste is leached with benzene and ethanol mixture 2:1 volume by volume at 60 degree centigrade for 3 hours. After leaching, the residue is dried in a hot air oven at 105 degree centigrade to a constant weight of 1.8 gram. This dried material is put in a flask containing 150 ml of N by 2 NaOH solution. The mixture is boiled for 3.5 hours with recycled distilled water. After this, the residue is washed with distilled water till all the sodium ions are removed and dried to a constant weight of 1.3 gram. Determine the extractives and hemicelluloses content of this waste on dry basis. If moisture content of the waste is 15%, determine these values with respect to original sample. So, initial weight 2 gram it is given, weight after extractives is 1.8 gram it is given, because the first operation is related to the exclusion of the extractives. So, we are getting 1.8 gram. Now, weight after hemicellulose separation is also 1.3 gram, the second step which was given, that is to remove the hemicellulose. So, that is equal to 1.3 gram. Extractive content we are getting MO minus M1 by MO into 100. So, this formula we have discussed in the previous class. So, here we are getting 2 minus 1.8 into 100 divided by 2, 10%, and hemicellulose content M1 minus M2 into 100 divided by MO. So, 1.8 minus 1.3 into 100 divided by 2, so 25%. And with respect to original waste material, the extractives and hemicellulose contents are say 85 by 100 into 10%, 8.5%, and hemicellulose content 85 by 100 into 25%, that is equal to 21.25, because it has some moisture content. So, if we consider it on original waste material basis, then these values will be reduced to some extent. Next, problem 4. COD analysis of a wastewater sample is carried out through chemical method using N by 10 potassium dichromate solution as reducing agent. Excess dichromate is titrated against ferrous ammonium sulphate. 100 ml of wastewater sample is used. The titer value of ferrous ammonium sulphate are 50 ml and 75 ml for original sample and blank sample respectively. Determine the COD of the sample, assume there is no interfering element in the sample. So, this is a problem of COD analysis, and for this we have the formula COD is equal to 8000 into B minus S into N divided by sample volume. So, here 8000 into B is nothing but B is the volume of FAS used in the blank sample as provided here 75 ml, and S is nothing but the volume of FAS in the original sample, and N is the normality of the FAS. So, here 75 minus 50 and normality is given N by 10. So, N by 10 0.1 divided by sample volume is 100 ml. So, we are getting this equal to 200 mg per liter. Problem number 5, statement is 1.5 gram of a solid waste is kept in the bomb of a calorimeter. The initial and final temperatures of water in bucket are 23 and 28 degree centigrade respectively. The bucket was is titrated against N by 10 Na2CO3 and the titer value is 2.9 ml. Sulfur content in the solid waste is 2%. Per 45 C10 NiCr wire is used to ignite the waste sample and 4 centimeter of the wire is fused. The water equivalent of the calorimeter is 2402 calorie per degree centigrade. Hydrogen content of the waste is 8%. Calculate the HHV and LHV of the solid waste. So, this is the problem related to determination of heating value, and we will discuss and we will solve it. So, to understand this, we will have some discussion on the principles of the determination of heating value. Say, to determine the heating value, initially small amount of material, say 1 gram, is taken in a bomb calorimeter and it is combusted, and the heat released during the combustion is taken up by some water, and the temperature rise in the water and the bomb calorimeter material is measured. That means, the heat given up by the material due to the combustion is taken up by the water and the bomb material. So, this is the principle, and by that way we by measuring the temperature difference we can calculate how much heat is released during the combustion of unit mass of the solid waste, and we can determine the heating value. And that heating value in this case is high heating value, because in this case the small amount of material is used and excess oxygen is provided for complete combustion, and then the flue gas which is generated, that is again cooled down, because although local temperature is very high, but the volume of the heated gas is very less and outside water volume is more. So, the almost all heat is transferred to the water and into the bomb material, and there is slight temperature gain. So, we are assuming that since the temperature is below 100 degree centigrade, so all moisture produced during the combustion of the material is already converted to water. So, the amount of heat which is we are getting or we are able to recover, that is the total heat or the high heating value we are getting through this instrument. So, this is the photograph of the bomb calorimeter. So, here the crucible, the weighted amount of material is put here. So, it is around 1 gram. So, after that this is put into this bomb, and after putting it here the lid is tightened, and then from this we have some connection one way valve where we can send oxygen and pressurize it. After that then we put it inside this water, and in this water bucket we put some water around 2 liter water, and then this is put inside this calorimeter, and where this some firing arrangement is there. So, when the material is there, there is some filament. So, these two end we have for electrical correction. So, an electricity will be provided. So, this filament will be burnt and the material will catch fire. So, when this material will catch fire, combustion will take place and heat will release, and that heat will be dissipated through this bomb material, bomb wall to the water inside this bucket, and this temperature will be measured by this temperature measurement device. So, this is the principle which is followed in the bomb calorimeter. Now, you will see by the experiment which I have mentioned here. So, after putting it inside, we will start firing. So, initially the temperature of this calorimeter will increase and it will attain a constant value. So, there will be some differential temperature we can get, it will be coming into equilibrium within few minutes, and then we will be getting the del T value. So, we will be calculating ms theta. So, that is equal to mass into specific heat into del T. So, that will be the heat taken up by the water body and this one bomb. So, that will be following to measure the heat released by the combusted material. So, after this experiment, the following data should be available at the completion of test in an adiabatic calorimeter, that is TA, temperature at time of firing, connected for thermometer scale, corrected for thermometer scale error. So, we have to correct if there is any error in the thermometer measurement, and TF is the final maximum temperature, again some correction is needed, or nowadays we can get del T also, differential thermometer is also available, and in this case the heat which we get during the heat which is released here, it is transmitted to the water, and by del T change we calculate the heat taken up by this, but which heat is taken up by this water and the bomb material, that is not exactly produced during the combustion reactions only. It has some contribution which are not from this combustion of this, but from other sources also. What are those sources? One is this crucible which we are using, that will also be burnt and it will also release some amount of energy. Number 1, if there is any sulphur, the shocks will be produced. So, that shocks again inside this bomb and the water will be condensed, the vapor will be condensed. So, that will give up sulphuric acid production. So, that will also add some amount of heat to the total heat which will be taken up by the water, and acids, some nitric acid can be formed, and that some amount of heat is also generated due to the formations of this acid, and we need to correct this contribution to calculate the exact heating value of the material. So, if we see that C1, C2, C3, another parameter we will get. What are those parameters? C1 is the milliliters of standard alkali solutions used in acid titration. So, to determine the value or contribution of the heat generated during acid titrated, during acid formation, for that after completions of this bomb calorimeter test, we will be open the lid and then we will depressurize it, and then we will open the lid and then take the material out, and then this bomb calorimeter wall will be washed, and then that washed will be containing the acids which was deposited on the wall, and that will be titrated against the alkali solution. So, that what is the ml of milliliters of standard alkali solution used for acid titration, that we can generate through the experiment, and C2 is the percentage of sulphur in the sample we can determine, and C3 in the centimeter of fused wire consumed in firing. So, before starting, what is the length of fused wire we are using, and after experiment what is the length of the fused wire unburnt. So, that difference will the burnt or used. So, heat has been released from that. So, that heat we have to compensate, we have to consider for error correction, and m is the mass of the sample in grams, how much amount of material we are using, that we can also calculate. So, this data we will be able to generate. Now, if you see after the combustion, heat is generated H1 and this is taken up by the water and the bomb material. So, this is water and bomb material. So, if we have m mass of water mw SW del T m1 S1 T1 ms del T. So, heat taken up by this water plus m bomb material and S bomb material and del T. So, this is the heat taken up H2 H3 taken up by these two, that is water and the bomb material. So, that we can get total heat taken up, that is equal to del T is common and m W into S W plus m B into S B. So, for a particular bomb calorimeter, these material are fixed, their material of construction, their size are fixed, and this bomb is also fixed, their volume are also fixed. So, these two terms are constant. So, that is nothing but W, that is called that water equivalent. Okay. So, this is the heat taken up, and what is the heat released by this material if you have m gram of material. So, m into H, that is the heating value. So, m into H, that is the heating value, that is high heating value, that is equal to this del T into W, but as we mentioned that this is not exactly the amount of heat which was generated during the combustion, it also adds something. So, we have to subtract those because of this your E1 error correction, E2, E3. E1 is from the due to the C1, E2 is due to the C2 and E3 is due to the C3. So, then this correction, by doing this correction we can calculate the actual heat which was generated during the combustion. So, high heating value H will be del T W minus E1 minus E2 minus E3 divided by m, where m is the mass of the material taken in the bomb calorimeter. So, this is the process we follow, and by using this formula we can calculate the heating value. But now the W, how can we get the value of W? W value can be measured using the same calorimeter and using a known substance. Now, this substance will be known. So, we know the heating value of this substance. Okay. So, that is the standardization or the sorry. So, this is the calibration of the equipment we can say. So, in this we used a known material and combust it, and in that case we know how much del H is there, how much heating value is there. So, we will be putting this formula, we will be calculating E1, E2, E3, M we know. So, in that case we will be getting the value of del T into W. So, we can also get the value of W like Hm plus E1 plus E2 plus E3 divided by del T. So, that way also you can calculate the value of W, and this is done prior to the applications of the bomb calorimeter and performing the same experiment using a known compound whose heating value is known to us, like say benzene is used. So, how we will do then, how we will calculate the gross heating value, then this formula just we have discussed, and how we will calculate the E1, E2, E3, that we have to know. So, E1 is the correction in calories for heat of formations of nitric acid, just we have mentioned, that is equal to C1 calories. If C1 is the milliliter of n by 10 NaOH solution, then this C1 will be here as E1 in calorie unit, and if E2 is equal to 13.7 into C2 into M, where C2 is the sulfur content in the material and M is the mass of the material we have taken for the test, and we multiply it with 13.7. So, that calories will be our E2, and E3 will be depending on the type of materials which we have used for fusing purpose or fuse wire material. So, like if it is a par 45 C110 nickel chromium, then that will be 2.3 into C3, where C3 is the length of the fuse wire which was combusted during this process in centimeter unit, and this equal to 2.7 into C3, where the 34B and S gauge iron fuse wire is used, and this equal to 0 when 34 gauge or finer platinum wire is used. So, these values will be provided by the supplier of the Bohm calorimeter. So, now knowing all those things we can calculate the Ag values knowing the value of W. So, W can be determined by standardizing the calorimeter using a compound whose heat of combustion is known, basically benzene is used. So, this is the standardization procedure we have mentioned. So, that is W is the energy equivalent of the calorimeter in calories per degree Celsius. So, these are the different methods we have already discussed. Normally 0.9 or 1.2 within this the benzoic acid is used for the determination of W value. Now, let us see in our problem statement what are the values. So, as per our problem statement we know that high heating value will be T into W minus E1 minus E2 minus E3 by M, and in this case the M is equal to 1.5 gram it is given, and C1 that is 2.5 ml standard alkali is required, and C2 2% sulfur, and C3 is equal to 4 centimeter of air, the fuse air, and T is equal to 28 minus 23 that is equal to 5 degree. So, that is equal to del T basically, and W equal to 2402 calorie per degree centigrade it is given in the statement. So, E1 will be how much? It will be related to C1. So, this equal to 2.5 ml into 1 calorie per ml. So, 2.5 calorie. Then E2 will be 13.7 into C2 into M calories that is equal to 41.1 calorie, and E3 2.3 into C3 that is equal to 9.2 calorie, because the fuse air which is used that has this formula. And then what will be the Hg? That is equal to Tw, that is mean 5 into 2402 minus 2.5 minus 40.1 41.1 minus 9.2 and divided by M that is equal to 1.5. So, we are getting 7971 calorie per gram, 7971 calorie per gram. So, this is our we are getting gross calorific value or high calorific value. So, net or low calorific value Hn we will be having by some empirical relationship we have discussed in the previous class. So, that is 0.555927 into 1.8 Hg minus 91.23 into H, where this Hg is the gross heating value and H is the percentage of hydrogen. So, in our previous statement percentage of hydrogen is given. So, we will multiply this. So, we will use this formula and keeping these values of Hg that is equal to 7971 and value of H as 8% it is already given. So, we by this calculation we are getting 7570.59 kilocalorie per kg. So, now the problem is solved, and then problem number 6. So, the statement is to determine the water equivalent of a Bohm calorimeter 1.1651 gram benzoic acid sample, high heating value 6318 calorie per gram was used. The experiment produced a net corrected temperature rise of 3.077 degree centigrade. The acid titration required 11.9 ml standard alkali and 8 centimeter of per 45 C10 nickel chromium fuse wire was consumed in the firing. Determine the water equivalent of the Bohm calorimeter. So, just discussed. So, water equivalent we can calculate by this formula H into M plus E1 plus E2 plus E3 divided by T. Now, in this case H is given, M is given, C1 is given, C2 is very important because we are taking pure benzene. So, we are using benzoic acid. So, benzoic acid does not have any sulfur. So, sulfur content is equal to 0 or C2 equal to 0. So, E2 will also be 0 and C3 is 8 centimeter as it is given. So, T equal to or del T equal to 3.077 degree centigrade. So, by putting this value E2 is becoming 0 and E1 is certainly 11.9 into 1 that is equal to 11.9 calorie, and E3 is equal to 2.3 into C3, 2.3 into 8 equal to 18.4 calorie. So, W equal to Hm that is 6318 into 1.1651 plus E1 that is 11.9 plus E2 equal to 0 and E3 is equal to 18.4 and divided by the temperature rise. So, that is 3.077. So, we are getting 2402.1 calorie per degree centigrade. So, that is the energy equivalent of the Bohm calorimeter. So, now we have solved all the problems up to this in this class. Thank you very much for your patience.